Okay, back to Andreas Hildebrand. I'd say he's a man who needs no introduction because I just did one an hour ago. So we're going to let him take over the stage and talk about synchronization for ST2110.
Very good. Thank you, Wes. So, my name is Andreas Hildebrand, working for LC Networks, the Ravenna guys. I skip over that slide because you've seen that in the previous presentation. Let's just jump right into the topic. We are talking about synchronization. How does synchronization work in general in 2110, and how does it specifically apply to audio streams? Because we want to have sample-accurate synchronization throughout the facility. Let's look at some general requirements first, which affect the precision requirement of synchronization and what we need to achieve. In general, in any broadcast-related or production-related environment, we want to have media bit transparency. So we don't want to deal with you changing our precious media data. So we need to make sure that whatever we do, the media gets through with full bit transparency. That doesn't sound like a requirement for synchronization yet, but it is. So we can't use sample rate conversion, and we need all streams, basically all devices, to run on the same media clock. And not just nominally at the same media clock, but actually the very same media clock. You know all this. Oh, we have a 48 kilohertz device here. We have another 48 kilohertz device there. We just pull the AES3 line, both run on 48 kilohertz, and what happens? It clicks. So we don't want to have that. And also, of course, we want to be able to run, because it's a universal purpose network and a general purpose network, we want to be able to run different sample rates on the network. Of course, also different media formats. And these should all be transported in a bit transparent manner. So we don't want to set the whole network to run 48 kilohertz and then force on the input a 44.1 kilohertz signal to be converted to 48 kilohertz. Furthermore, we want to have a determinable and most probably also a low end-to-end latency on a network. Determinable means something we can predict. We can settle on and fix it to a certain value, and of course low latency, because we don't want to wait for 2 seconds before we can process the incoming audio. And of course, we want to be able to time align all the streams on a network with respect to each other. If I have two microphones sitting in a stereo environment and they send off their streams individually to the network, I want to be able to actually sample accurately correlate these streams when further processing. So these are a few important requirements. And out of that, in addition to that, we all know about this house clock, this Genlock reference, Blackburst, word clock, whatever, running around the whole facility. Of course, if we have a network, we want to get rid of that as well. So we want to use our network as the transport medium for our house clock. So from the requirements, we can see clearly that clock reassembly from incoming stream data is absolutely not the way to go. So we can't just reassemble or regenerate the clock from one single incoming stream. That's not appropriate at all. Also, the distribution of master clock beats on the network with whatever scheme is not sufficient, because we need time. If we want to align streams, we have to have time on the network. And from all of that follows that we need a common understanding of absolute time in each and any participating device. So we need to have somebody who is distributing, or some instance who is distributing wall clock time, and this wall clock time needs to be present in every participating device. Only then can these requirements fulfilled. What are the accuracy, the precision requirements anyway? So if we look at our use case, we can identify that we have the most, or the highest accuracy and precision demands from audio actually. We want to achieve sample accurate alignment of individual streams on the network. So that means we need timing which is accurately enough to at least plus minus half a sample, so half a word clock period. So the time we use, the reference needs to be at least as accurate as plus minus half a sample, which translates into these nice numbers. So you can see with 48 kilohertz, plus minus 10 microsecond, which is about half a sample, would be okay. But if we, for whatever reason ever, go up to 192, we already need 2.5 microseconds precision in order to match half the sample clock. Now, the other requirement, remember, was the distribution of the word clock reference. Now, we have a standard for the precision of a word clock master, which is AES11, and that calls for a maximum allowed jitter and wander of the reference clock of plus minus 5% of the word clock period. That translates into even further numbers, which we want to be able to match with our network. So 1 plus minus 1 minus microsecond is mostly sufficient for 48 kilohertz, and well, it goes down to plus minus 250 nanoseconds at 192 kilohertz. So how do we deal with that? How do we achieve this? Well, all nodes have to run local clocks. We know that by now. These clocks need to precisely synchronize to a common wall clock, and we use Precision Time Protocol 1588 in the PTP version 2. For that, remember, there is a PTP version 1 standard out there, and it's also being used by some gear, but we need to use PTP version 2 because that's what we all settled on for AES67 and 70, and these both versions, unfortunately, are not compatible. So PTP version 1 cannot run with PTP version 2 or vice versa. They can run on the same network, but they are separate, let's say separate protocols. Although they are similar, you can't, a PTP version 1 device can't run on PTP version 2 protocol and vice versa. So, and then those who watched my presentation half an hour ago or an hour ago, the media clocks can then generate it locally from the local synchronized clocks. Here's another picture, and in order not to repeat the other one I had, we have a master clock, which in most cases is referenced to a very good, precise external reference. The mighty satellite gods about us serve us very well here. We have slave clocks, and they are all synchronized utilizing the PTP version 2 protocol. From the clocks, I can use any desired media clock, and once I have precise time in all my devices, all the clocks are absolutely identical. Not just frequency-wise, but also phase-aligned. That's the general picture how we generate media clocks which are precisely aligned with the precision down to what we require, because PTP can actually serve that. So, next step is, when we have time in the devices, we can of course generate any desired media clock we want. We can generate 44.1, 48, 96 or 90 or whatever for video kilohertz we need. And of course, on the same network, I can operate multiple different media clocks. I can't necessarily distribute a 44.1 stream to a 48 kilohertz configured receiver, but the streams can live there so that I can concurrently work with 44.1 and 48 kilohertz audio streams, and of course also video streams, which yet have another media clock, basis media clock, on the same network, because I have decoupled the protocol from the actual media clock generation now. The phase accuracy can be matched with PTP. Remember, 192 kilohertz reference clock would require 250 nanosecond precision. PTP version 2 would allow us to go down to a dual-digit nanoseconds precision. In some cases, that would require PTP-aware switches. PTP-aware switches are those switches which natively can identify PTP packets on a network and can correct any resilience or transport duration within the switches, so they add an offset value to the timestamp of the PTP packet in order to tell the downstream devices how long that packet had been resilient in the switch. So it doesn't matter if the PTP packet is actually forwarded at the very next moment down to the egress port, but the offset value can now tell the downstream devices what was the resilience time in that particular switch. So boundary clock or transparent clock switches are there. You can see them all over the place. Most switches now, at least those the large ones, actually support PTP natively. And if it comes to synchronization across facilities, PTP doesn't by nature travel very good across wide area network connections because it's very prone to packet jitter. But the solution here is very simple. Since those satellites over us span around the world, we can just use local GPS referenced grandmasters in every location, and then we have the absolute same time in each location by distributing PTP locally to this environment, and don't let the PTP run across the wide area network link. So it's local synchronization, reference backwards to the same reference source. Now, the next trick kicks in. We have time, we have absolute accurate media frequencies. Now we want to be able to determine when a particular audio sample, for example, or picture frame, actually has been generated, has been sampled, or has been started. So whenever the microphone or any audio device gathers an input sample, we want to know when does that sample has been acquired, has been ingressed into the system accurately. Now, the devices all have time, right? They have precise time, down to the dual-digit nanoseconds. So at the very moment a sample is being gathered from the input side of things, it receives an accurate timestamp. So once that sample travels onto the network, any instance following down, receiving that particular stream, can exactly know when has a particular sample been generated. So that is, well, technically wise, it's not every sample which is receiving a timestamp, but for now, to understand this, every sample has an accurate location or reference to absolute time down into dual-digit nanoseconds range. Any sample, any frame, any information on the network. So once we have that, oh yeah, let me explain how this actually works. We have three types of clocks in the system. Those who watched the presentation earlier already know about these three types of clock. I'll try to explain it here again. We have the wall clock and its local copy in each device. That's the first clock, the local or the wall clock time, the system reference time, the GPS reference time. We have the media clock that is derived from the copy of the master clock. That's derived from the local clock, which is a copy of the master clock. So the media clock, let's say 48 kilohertz, directly follows the system reference, the wall clock time, in all the devices, independently but absolutely in sync. And then we have the stream clock, yet another clock, because RTP, as the transport protocol, has RTP timestamps with linear audio. It's indicating what is the precise timestamp of the first sample in that RTP packet. And nicely enough, we don't have to put in there PTP timestamps, because with linear audio, the timestamp is formatted as a clock counter. So we have 32 bits of timestamp. We'll explain that in a minute. We count clock counts actually here. This is the picture I had up. Who attended the presentation an hour ago? Just hands up, quick hands up. So some of you have seen that, some not, right? Just a very quick run-through, because it's just telling you basically the same. We have the grandmaster, we have the sender-receiver device, we have local clocks in these devices, and they are copied with PTP. The wall clock is copied with PTP into the local clocks. The nodes independently generate their media clocks out of precise time. Sender and receiver do that. These are fully in sync. And now we instantiate the stream. The stream data travels across. The stream yet has another clock, the RTP clock, the stream clock. Usually it's required to have a random offset because of the underlying standard, RFC 3550. They say, please use a random offset. That's because when you use encrypted streaming, that part, the timestamp, is inside the encrypted packet. If we would have a known reference when just looking at the stream, it would be prone for crypto attacks. So the guys ask for a random offset. However, the receiver would have to know that offset in order to relate that stream back to the overall system time, and that is being transported with the SDP as an information in the SDP. So with this line, the transmitter tells the receiver what's the random offset of that particular stream, and the next stream it instantiates gets another random offset. So SMPTE found this is too complicated. We don't need this. We don't want this. We are not aware. We are not afraid of crypto attacks. Let's make things easy. We require everybody to use a zero offset. So all the streams from the clock, from the perspective of the clock, look just the same. They have a zero offset, so they don't have to transport the SDP, the information in the SDP anymore, because by definition, it's zero. It doesn't make things really more difficult or less difficult or whatever, and it doesn't affect the synchronization at all. So it's not better or worse in terms of synchronization. It's a technical thing which would just be implemented in audio devices which support the ST2110-30 standard. So we have three different clocks just to get this, the wall clock, with the local clock, we have a media clock, and from the media clock we have stream clocks, and within ST2110-30, all these clocks are fully running in sync and any stream fully relates back to the master clock time. Here's what I just started to explain a slide earlier. Let's look at the RTP packet. This is an RTP packet. Now it has a header, a fixed 12-byte header, which has some interesting data in it. There's some options which may or may not be in that packet, and then there's the big bunch of samples or picture information, so the media payload. And if we look at that packet, we have the header, 12 bytes, and this payload, and in the header, there's the timestamp information. It's 32 bits, 4 bytes. And for our payload format, for linear PCM audio, these 4 bytes are used as a media clock counter. So what actually happens is, this is an increasing counter, and guess what? With 48 samples of payload in each packet, which is the requirement of AES67-30, what would you expect in the times from one packet to the other? How would the timestamp numbers look like? Easy. It's an increment of 48, because it's always indicating where is the first sample. What was the media clock count when that sample had been generated? So basically we have the media clock count for that particular first sample in that packet, looking at it as if that stream would have been generated, the stream would be instantiated on the 1st January of 1970, because that's the time origin of PTP. Of course, the clock count advances, you know, and with 32-bit, you can see we have rollovers once per day. But since we know the exact time of day, we can easily calculate modulo 32, where are we exactly with respect to the day to day. If we see a clock count, when had the stream been generated? And believe me, no stream ever is longer on a network than 1 day. So this is this is always gives you a very unique identification. When has this particular sample, which is the first one in the packet, been generated? No stream runs for 1 day on a network. So this is a very precise and very straightforward theme. So that's how the relationship of that particular packet with respect to system time is being transported. And there's some math behind it, but the math is not very complicated and should allow the receiver to exactly identify, okay, I'm receiving that packet, the first sample. When has that been generated, wherever it had been generated? Because it's written here as the media clock counter, referring to the system clock, to the overall clock time of the day. So now we know everywhere, for every individual sample, when has this accurately been created? Now, once we know when it has been created, the magic trick is now, first of all, on the receiver side, we can fix or configure a determinal or fixed playout delay. Why would we want to have a playout delay? Well, because first of all, samples need to be gathered before they can be put into a packet. 1 millisecond packet time means 48 samples. The sample has already latency of 1 millisecond at the transceiver side. Then it's transported across the network. Guess what? It's not just like a wire where all the bits flow nicely isochronously down the network. It's packets. And there are a lot of packets on a network. And sometimes packets get in front of you when they need to get forwarded, so packets receive packet jitter. So at the end of the chain, a receiver always needs to cope with a certain amount of potential jitter. It needs to implement a receiver buffer. And within that chain, a system, for now, has to tell the receiver, or a human or an administrator, what is the desired play-out delay or latency for that particular stream, taking into account any potential packet jitter it may have received during transport on the network. And we fix that to a suitable offset, calculating for potential network jitter. Basically, that can be individually for any stream. I give an example. For example, we have a front of house man, a singer, a performer, whatever. He needs in-ear monitoring. So we have the microphone. We want to have a relatively short packet time and feed that particular stream back on the shortest possible way so that the overall end-to-end latency stays, let's say, below 2 or 3 milliseconds. That is acceptable by most people. Now, front of house needs the very same content. Do we have to create another stream just because that has a different processing delay? It doesn't have to have 2 milliseconds. It can work with 5 millisecond processing delay because there are other streams coming from the stage or elsewhere which need to be correlated maybe. No, it can receive the very same stream because it knows when it's created. We can still work with a 5 millisecond processing delay in order to be able to arrange it with other streams. And then there's the OB-WAN outside. He also wants to have that direct stream. He can receive the very same stream. It knows when it's generated, but he said, okay, I have a relaxed processing requirement. I can use a 50 millisecond processing delay because there might be more switch stages in between, or it might have to correlate with any other ambience or process signal, and so on. So particularly, one single stream can be received wherever it needs to be received with individually suitable, appropriate latencies. Only if I want to correlate streams, now this is the tricky part. If I want to correlate streams with each other, let's say I have 2 microphones capturing a stereo image independently, setting it into independent streams on the network, and I want to be able to correlate that on a mixing device, then I need to see a look at the incoming stream timestamps. And now we know when any individual sample had been generated by looking at the RTP timestamps, comparing them after the math to the wall clock time. I can now exactly determine I want to have a 2 millisecond processing latency in order to cope with any potential network jitter. And now I can exactly match the samples which are stored in the packet in my playout buffer so that samples which have been gathered at the same point in time can actually correlate it for the further onwards processing. So that's the magic behind the timestamps. This is why we all need time in the system. If we wouldn't ever have the requirement to correlate streams with each other, the system would have been very, very simple. We just subscribe to an RTP stream, which we know is fully synchronized to our media clock, and we just look at the stream, build a small buffer. Let's say we watch the stream for a few seconds, see, okay, the maximum jitter amount is like, let's say what, 50 milliseconds, so build a playout buffer of 70 milliseconds, then I'm on the safe side, just to sell something now. And then let the stream run. But we never know when it's actually being played out with respect to other incoming streams. That's why we need the precise, accurate time in there. Here's a picture of the typical production workflow timing. Let's see, here's a camera capturing image. We forward it to a processing or vision mixer. There's processing time, we have another forwarding to another processing, whatever, a device, and so on. Once it finally reaches a usage device, so let's say a display or whatever, something where you actually need to synchronize streams again. So we have link times of streams, processing time, and so on. Now, we also have an audio stream coming from a microphone, let's say. Link time, processing time inside a mixer, and then there's a point in time we want to play out that audio. And of course we want to play out that audio in correlation with the video. And now the trick is, as just explained, because apparently that stream reaches the speaker quicker, faster than the video stream, also of course for packet times and frame zoom, whatever things are in the processing queue. We may have to delay the play out of the audio stream on the speaker for more than what would be required to cope with the packet jitter in order to nicely align it to what is being set as the overall link time for the video signal. So all this speaker device needs to have a suitable buffer to hold up the incoming packets and align them for further processing, this time's play out, to be aligned with any other stream, audio stream or video stream. And this goes all by looking at timestamps and wall clock time. Actually, in our AOIP or video over IP environment, all these devices have to have buffers because packet jitter is appearing everywhere. So any stage which is receiving an IP stream needs to have a packet buffer. How large this would be, this is nothing which is specified in the standards actually. It's more looking at, okay, what's the application, what's the network providing as performance capabilities, with what packet jitter I would have to cope. Do I have to line up or align several streams line-wise or even frame-wise? This all would determine what the manufacturers decide to have as buffers available inside their products. But we need this. We need this buffer at every stage. We can't go without it. Now, you have seen there were various processing stages. we have various streams between the processing stages. And now something else kicks in. The problem is when we generate a stream on a network, we have its origination timestamps, we have the stream clocks and everything nicely defined. So as long as we deal with that particular stream, we can align that to any other stream on the network, unless we have a chain where a processing of the received stream happens and a new stream is generated, because it's a new stream. It's new, it's processed data, it could be mixed data, it could be mingled with something elsewhere, or just a processed content of the original content. So we have a new stream on a network. And guess what? That new stream has its own origination relationship. So the timestamps carried in the RTP for now, at the first moment, are the timestamps which tell you when this stream of the second stage had been put onto the network. That's what is described here. The problem which we have to look at is that any stream leaving a processing device in the chain is a new stream. Any new stream is newly aligned to the wall clock time, of course, and the alignment of the original essence by design, by technology, is lost, which apparently makes it not quite as easy to align the processed video image, let's say, with the somehow processed audio again. Because now at the end device we see streams which are not the original content streams anymore. And the timestamps carried in these streams are not those reflecting the original essence. So what are the possible solutions for that? I don't have a solution which I can tell you that is the solution, because this debate is going on and it's not very easy to solve, but we need to understand it in order to see, okay, we can make the facilities, even if there's no fixed standard for that right now, we can still make facilities work, as you can see over here. This is all working with sync and stuff, but we need to see at possible solutions. It would be possible to use the original timestamp alignment in the outgoing stream. So let's say force the RTP timestamps of the process streams to carry the timestamps of the original stream. So as let's let this process stream look like it was the original stream. Questions appear. Offsets may increase, they might be too large for downstream receive buffers if I back relate the stream to it. Then if I have a mixing device, for example, which timestamp would then serve as the reference timestamp? Is it an essence which can be related to the to any of the incoming essences at all? Or would I deliberately have to instantiate a new stream? And how's that then referenced to any audio maybe? And then the question, if you look a bit deeper, if you would go with this solution, how would the processing device, the host device, which would have to use this solution, how would it know the exact relationship between ingressed essence and outgoing essence? From the network plane where we have the reference, essence is routed into the device. And something happens with there in the device. And then once of a sudden, some essence appears at the egress plane again, which is our reference plane for the timestamps. So how would that device on that network plane know what was the exact duration of that essence inside my device? How would it know? It would only know from a management layer above. Someone has to tell the system which timestamps to use. So others say, okay, another solution is, okay, why not carry the origin timestamps as in-band metadata? So throw the original timestamps inside the payload. Well, you could do this. You can either define a new payload format. Remember, we have for audio L24. So where should the metadata go? It's L24. So we have to define a new payload format. Or you might want to use RTP header extension mechanism. You remember the RTP header? It had a field in between, which I didn't highlight, optional RTP header extensions. However, that may cause other problems in turn, because if there are header extensions, they are not defined what they carry. So if somebody receives that stream, it doesn't know by default what to do with it, so it could skip over. Well, within 2110, we could define, okay, header extension look like this. And then somebody else tells us, oh, I don't only want to have the origin, I want to have some other metadata in that. So it changes, it increases, decreasing the payload size. So once of a sudden, we can't transport what we wanted to transport in one packet anymore. We have to split across packet, make the stream smaller, whatever. So it could be a possible solution, but it causes other problems. Of course, we can carry the origin timestamps as out-of-band metadata, just as we could transport the media clock offset when it's random out of band with the SDP. So it's not changing our payload format, not changing our stream, but transporting this out of band. That means with another protocol or another information in the SDP whatsoever. If we look at what's currently going on, there's a group in the AES, it's called X242. It's dealing with real-time metadata transport, which could be sample accurately aligned to samples again, to AES67 samples. That would cover for much more use cases, of course, it's just transporting the original alignment. But there is work out there which might help solving this problem. So what can we do for now, actually? We are aware of the problem, what can we do by now? Current solution, maybe just an intermediate solution, maybe a more durable solution at all is leave the alignment task to a management layer. Whatever that means. What is a management layer? Can be the human brain, just looking at a picture, dialing in the offset to have lip sync again. We know all this from the past days. Or let the processing devices tell a broadcast controller, okay, my resilience delay of essence is 2 milliseconds. So the broadcast controller knows and has to tell the downstage devices when it comes to setting up the playout delay, these particular values in order to have a full alignment of streams again. So what we do for now is we leave this to a management layer. That is not defined, and there are so many guys out there also in the showcase who have broadcast control systems. They could deal with this, and they do it by day anyway. It would just need a few more definitions how to actually tell the broadcast controller what the duration or what the processing delays are. And some of this work is already being tackled by the NMOS group. So we are aware of this problem, and we are on it, and I'm sure we will come up with something which is then generically useful. I'm not a friend of, realigning RTP timestamps, but that's not what they were meant for. I'm neither a friend of using header extension because they cause another bunch of problems. I'm a friend of having out-of-band transport because that's more flexible, gives more options, more solutions, or leave it just to a management layer here. So as I said, devices can report the processing delay, and the broadcast controller can configure the required receive buffer delays on the participating receivers to have an exact sample rate alignment there. So basically, when we look at these pictures, we will add something like a broadcast controller which deals with all these individual processing delays, but most important, with that one which is required to have here the same delay as in the processed stages of the video signal. So that's the suggestion for now. That's the intermediate solution everyone is working with. We will see if some more comes up to help this scheme, or even if we settle on something standard-wise where we can preserve some original timestamps. But I can tell you, implementation-wise, it's really difficult to transport the original essence timestamp through unknown processing stuff inside the device to match the egress stream again, regardless which solution you are choosing. That's it from my side. Sorry for not being able to run in another 5 minutes again, but thank you very much. I know it's a very difficult topic, but it's an important one.
Well, thank you, Andreas. Have time for one quick question. Anybody have anyone? Yeah.
Oh, sure, of course.
When the broadcast controller is configuring the buffers, does that mean a human has to measure the jitter and tell the broadcast, or is there an automatic process for measuring jitter?
As I said, by now there's nothing standardized. So it might be that there are automatic means that would allow the broadcast controller to align it by, for example, knowing the processing times, the resilient times within the devices, because they usually know and can tell the broadcast controller. At least it's the way to look at the picture and see, okay, how does it work? And then you have sort of, numerical entry things and can nicely align it, and then you have the number and can apply that to other devices as well. So there are no standardized means out there. I would assume that as we have these things over here, that some of the broadcast controller manufacturers can provide a viable answer to that. But we are working on it to have something which is then at least sort of giving the information and or getting the information off the devices to a broadcast controller, just like we did with the NMOS, ISO 6 and ISO 4 stuff in terms of discovery, registration, and network control. So we're working that. I think they will come up with something which is viable and acceptable for everyone. By now, yeah, probably it's the dial. Well, not an analog dial, but a numerical dial, yes. All right, guess we have the next presenter. Thanks a lot.